Welcome to this tutorial on Scikit-optimize for LightGBM. This tutorial has been arranged for Kaggle's 30 Days of Machine Learning, an initiative to accompany machine learning beginners in 30 days training in order to become effective Kaggle competitors. Let me present myself. I am Luca Massaron. I am a Google developer expert and a long-time Kaggler. I started about 10 years ago doing various machine learning competitions. I'm still participating today in competitions because I find it quite enlightening about all the new technicalities in machine learning and a very good training for keeping myself in sharp with data analysis. So let's begin. In this talk, I will present to you how to do hyperparameter optimization with a special focus on Bayesian optimization, the most efficient and highly performance methodology for optimizing your hyperparameters of your models. I will also slightly introduce about LightGBM, which is a gradient boosting method which is quite effective and one of the power horses of most Kaggle competitors. Finally, I will provide to you an example tutorial you can reuse for your incoming Kaggle non-competitive trial with data and competition. So before starting effectively, I have to credit that some figures and examples have been taken from a book that I wrote with John Mueller, Machine Learning for Dummies, and also a part of explanation about the Bayesian optimization is taken from the Stumped, the Scikit-optimize website. So I refer to Gilles and Manoi, who prepared this tutorial in 2016. Let's start with hyperparameter optimization. As you may already know, machine learning algorithms have a lot of knobs, and success often comes from twiddling them a lot. These words comes from Pedro Domingos, in his very famous paper about a few useful things to know about machine learning, a paper that I suggest you to read because it's really full of insights about how to optimize and how to understand your machine learning models. This translates to the fact that actually, if you carefully think about your machine learning model, this is a mapping operation. It means that it takes your inputs and by a function, it translates them into a prediction, an output. Of course, the more related are the inputs to the outputs, the more success your operation, your mapping operation will have. Let's take, for instance, this functional form of a possible machine learning algorithm. So you have a y, which is your target, and your target is given basically by this very simple functional form. You have a beta 1 multiplied by your input x, and then you have a gamma multiplied by another parameter beta 2, which is multiplied by your input squared. Finally, you have the summation of another parameter alpha. Actually, if beta 1, beta 2, and alpha are learned by your algorithm based on the data you provide to it, your gamma, if it is an hyperparameter, will be completely independent from the data you provide to it. And it will be basically a choice of yourself. For instance, if in this case you provide gamma the value of 0, your functional form will be reduced to a simple line because the second term of a form will just disappear. But if you provide gamma with 1 or another number different from 0, you will have as a functional form a parabola. This is exactly what happens with all the hyperparameters that you can find to be set in your models. They actually change deeply how your mapping of your input values relate to your outputs. Let's take as an example a Scikit classifier, a support vector machine. A support vector classifier can take a various number of hyperparameters as input. And as you can see from the two panel examples, you can see in the above part of the slide, actually even changing slightly one of these parameters can have important effects on how the classifier divides the cases you present to it into classes. In this case, you have a toy example, but the effect on the real data can be even more important and quite different. For instance, in a support vector classifier, you have to decide about the C parameter, which actually is a penalty for complexity of a curve. You can choose between different kernels, from the linear one to the non-linear in different complexity form, the sigmoid, polynomial, the real basis function, and then based on the kind of kernel you decided, you can have to decide about the degree, which is the complexity for a polynomial form, the gamma, which is actually the influence of single examples on the curve, and on the coef 0, which is an independent term, which is significant for sigmoid and polynomial kernels. Actually, Kagglers that have quite good experience in modeling machine learning algorithms, since they know, as I presented to you about this example with a support vector classifier, since they know their models quite well, they tune such hyperparameters by hand. And actually, this is quite possible because if you concentrate on just of a few parameters which are important for your solution, and you deal with each one in turn in a bisection operation style, you can manage to tune your algorithm in a quasi-optimal way. Actually, using a bisection operational style, you explore, taking each singular parameter, smaller and smaller intervals of its values until you find an optimal tuning. This works quite fine when actually you have for each parameter a single sweet point. So the complexity of the landscape of the hyperparameters is not so, in the end, so sophisticated, and you don't need to try very special interaction between them. Though this is practical in some Kaggle competitions by very expert participants, for the majority of us, this is quite difficult. It can really work, for instance, with a simple algorithm like the k-nearest one, when you have just a few hyperparameters to tweak. For instance, here the dominant one is the number of neighbors that you have to take into consideration. And actually, you know theoretically that if you take a large number of k-nearest of neighbors for your k-nearest model, you actually are smoothing your decision boundary. So you are making more generalizable your predictions, at, of course, expenses of its adherence to the characteristics of the data you are providing. This can work very well, but for more sophisticated machine learning algorithms, this can prove very, very difficult. Besides tuning by hand, you have more practical options, especially if you don't know and don't want to, of course, inspect too much the hyperparameters you have to set in respect to your data. Grid search is the most obvious alternative. How does it work? It simply exhaustively searches through your hyperparameter space and it finds out the best combinations. So just imagine, for every parameter that you have to fix, you pick a set of values you want to test. Basically, it should be a closed list. So a list of all the values you have to test. Then grid search just combines all the possible combinations of these parameters values and test each of them. It is really exhaustive in the sense that it will just try everything that you told potentially to be tried. It's very simple, it's quite effective in certain cases, but it is really computational heavy. You can anyway deal with it in a parallel way. So the more processor you have available and the more memory, of course, you can use, the faster this operation can get. But it has some side effects. Therefore, let's have a look how it works here in this example. This example taken from Scikit-learn, we are going to classify the digits from the digits dataset. And using a support vector classifier, we will just focus on figuring out what could be the best hyperparameters between a linear model and a kernel model, the radial basis function. Since the linear kernel takes different hyperparameters from the radial basis function, you have to specify exactly how the grid search works by providing two different sets of values to search in case of a linear kernel and a radial basis function. This translates in, of course, an exhaustive search taking into account 4 possible values of the C hyperparameters when the kernel tests the linear, and then a combination between the 4 C values and 2 gamma values that you have chosen when the tested kernel is a radial basis function. It translates into a testing, exhaustive one, of about 4 possibilities for the linear one and about 8 possibilities of combination for the radial basis one. Just imagine if you have a more complex situation with more tested hyperparameters and, of course, more values. This could translate into a very long time in testing different possible combinations. For the moment, we have a simple model whose best result is using hyperparameters of C equal to 1 and gamma equal to 0.001, and the chosen kernel is the radial basis function. We can get in this way an accuracy tested by cross-validation of about 0.97 accuracy score. A solution recently found to testing, in respect of testing in an exhaustive way, your combination of hyperparameters is to use random search. Random search takes a different approach in testing hyperparameters because it simply samples the search space randomly. So you don't have a schedule actually of combination to be tested, but random search just picks them randomly, creating a different test for you every time you make a check on a combination. In this way, random search reaches a couple of objectives. First of all, you can control the number of tests you want to make. So if you basically don't want to spend more than 30 trials, you will just set your random search to a limited number of trials, such as 30, instead of testing all the possible combination. Then random search offers you the possibility to test a hyperparameter on values that are continuous. As we have seen previously, when you're using grid search, you actually have to define a certain number of options to be tested. But how can you choose them? If, for example, your hyperparameter takes values ranging from 0 to 1000, basically, or you test all the integers values between 0 and 1000, or you have to, in some way, based on your domain knowledge, just pick some possible options. Random search doesn't need that. It just takes a function sampling from that range of values, and every time it tests the value that is randomly picked. Also, this allows to ignore irrelevant hyperparameters. In fact, let's figure out that you have one hyperparameter that doesn't have so much effect on the results of your predictors on your data. In such a case, when you are testing it by grid search, you have to test all the values that you have in advance decided to test on that hyperparameter. And this can turn into a waste of time because you won't get any different results than testing just on the singular other hyperparameters. With random search, even if you are testing actually on a hyperparameter that is not effective, at the same time, you are also testing values of the hours, but making actually your time spent on that test much more effective. Let's see first an example of how you can set a random search on scikit-learn. In this case, what you have to do is just to define for C and gamma where to pick the values from. In this case, we have chosen a uniform log distribution. It means uniformly, it will just sample from the log values of the range you have provided. And this works perfectly, even if the kernel, the chooser one, is the linear one. Because as we know, the gamma hyperparameter won't actually work, but it doesn't, it's not so important for the random search, because when the tested kernel is the linear and it picks a gamma value, actually, since it's not working, it is testing instead on the C hyperparameter that it has chosen. This makes random search particularly effective. In this case, in this example, we just decided to test about 6 random picks. And in the end, since it could pick options from all the entire range of values of C and gamma, he found out that there is a possible combination with C, which is 338, and gamma, which is 0.00047 for always the radial basis function kernel, which is a little bit more effective than the values we have found by grid search. If you're wondering why, this picture of a possible hyperparameter optimization between two parameters will reveal you why. Let's imagine your model just picks the parameter alpha and beta. And if you plot all their possible combination on a scatter plot, you can figure out that if there is one single point of optimum, if you're just doing grid search, which is actually the points, blue points in this representation, you can actually miss it because you are just testing at very specific, precise intervals. Moreover, you are just testing in an exhaustive way. So for instance, if your parameter A alpha is not so effective, actually will happen that you are wasting time testing them. Random search instead is not limited by the construction of how the experiments are set in research and can pick randomly here and there. And it has more chance, of course, if you give it enough trials to pick up the right value. If you are wondering what could it be, the right number of trials to be done by random search, empirically we suggest to make a number of trials between 30 to 60. The exact number really depends on the number of hyperparameters you have to test and, of course, on the difficulty of optimization, because you can have hyperparameters that interact with each other, and you have some irrelevant ones and so on, and that really affects the number of tests you have to make. Basically, doing from 30 to 60, we have found that it is a good choice between the time it takes to make all these tests and the results you can get. Of course, sometimes luck is very important with random search to find your hyperparameters, but as we said, if you test enough, you can really find what you're looking for. Anyway, at this point, you may wonder if there is a way actually to leverage the information that you get as you explore the hyperparameter space, as actually many people are tuning their models are doing, because we are testing and getting our feedback and then decided based on that feedback where to test again. And also if there is a way to, of course, just be able to tune your hyperparameters in an agnostic way, that is without being an expert of the algorithm that you're tuning. And if there is also a way to really find a quick optimization, because as we said, grid search can really take a long time, and thus it has strong limitation, and random search can give you better results the more you try, but you have no guarantee that after a certain number of trials, you can get the result you are expecting. And the answer is actually yes, because we have Bayesian optimization formalized in this paper of 2012 by Snoek, La Rochelle, and Adams. Bayesian optimization is the answer for your optimization when you have little time and you don't want to fully get in deep how your algorithm machine learning algorithm works. I will briefly explain to you the key ideas behind Bayesian optimization, and then we can have a look at how it works by taking an example from the Scikit-optimize website. The Scikit-optimize package is our choice for this tutorial. Why? Because it's very easy to be used. It has an API which is fully compatible with scikit-learning algorithms, and actually it provides very good results using a Gaussian process. I will explain better to you now. The key idea behind Bayesian optimization is that it's very expensive, costly in terms of computation and time to test your machine learning algorithm on the data. So you have to minimize also the efforts you are making in order to figure out the best hyperparameters combinations. In order to do so, you just have to avoid testing your algorithm and instead creating another machine learning algorithm to test based on the results you get on the different hyperparameters combination you get. If you think of that, is something that really resembles testing by hand. You make a few trials, and based on that few trials, you figure out that actually you could test certain values with more success than others. Bayesian optimization does that because it records some initial tests, maybe doing randomly, And then he used such results in order to create a predictive algorithms that, given the hyperparameters of your model, can provide to you an estimate of what could it be if you tested different parameters. This is called the surrogate function and is built and refined as you go during your Bayesian optimization. It starts not having a clue about what to do, and that it improves on the way, getting better and better results. This process balances actually an exploration, because it will test different values along the way, with exploitation, because as it does the testing guided by the surrogate function, it will also find out solution for you to be reported. Surrogate function is not the only one at work in a Bayesian optimization. You also have an acquisition function. And in the case of the example I'm going to show to you, this is very easy. Acquisition function is the function that tells the optimization exactly what values to explore along the way. And it's based on the surrogate function. Let's see with a practical example how it works and why it is very easy in the example, in the tutorial we're going to propose to you. Let's take a situation where you have to figure out the hyperparameters of a very simple curve. You have a single hyperparameter, which is x. And based on the value of x, you can get a very different optimized value, different score, which is represented here in the y-axis, which is a fit from the model. Basically, the less the better. This is very important to recall. When you are optimizing a model, usually all the optimizer for hyperparameters takes that it is a minimization problem. This is true actually in most cases. Sometimes you may have a different problem, maximization one, but you can easily convert it into minimization. In this case, we have to find, since it is a minimization, the value for x that provides to you on the y-axis the minimum value. So basically, it should be around minus 0.6 or 0.7. But we don't know actually this curve. We have to find out by Bayesian optimization. In our example, here you see 4 panes, A, B, C, and D. After a few trials, maybe having done randomly, the Bayesian optimizer finds out that it has an estimate of how the model reacts to changing the parameters, which is not really far from actually how it really reacts our true function, but it still has differences. And what is interesting, because this surrogate function is based on Gaussian process, is it that it also has error estimates. So for every point of his reconstructed feedback from your model based on the hyperparameters, it can tell you at any certain combination what could be the results, but also how much it is uncertain that that will be the result. By summing the estimate with the error, we can get what is represented as acquisition function, for example, in the B panel. By summing them together, the algorithm can figure out that there is one point in its estimated surrogate curve that it could be very interesting to explore, because it's very promising. Its estimate value plus the error in the negative side gives you that it could be a maximum. So it tests it. Of course, it's not our maximum. It is just a local one. It is not our minimum, it's just a local one. But it provides the algorithm, the surrogate function, with an idea that is not necessary anymore to explore in that part. And instead, it is very important to explore our values. As we go on with the optimization, the Bayesian optimizer tests more and more areas of the curve, the surrogate function, representing the results given by different combinations of hyperparameters. Finally, it will find the point that minimizes the curve, and it will provide to you that it has no more uncertainty about what the minimum could be. So to recap, Bayesian optimization is a process of optimization based on a surrogate function, that is a function that should replicate the behavior of your machine learning algorithms at the change of your hyperparameters values. It is also based on an acquisition function, which, given the results that it finds out on the surrogate function, it will help the Bayesian optimization to keep on exploring by testing, but testing just the necessary extra points, extra tires, to lower its uncertainty that it is providing to you the right minimization value. So in such a sense, Bayesian optimization is very efficient. It will just take the trials necessary to provide to you the information you need. And as you can see in this reconstructed curve, the surrogate function actually still has some places where it is uncertain. But Bayesian optimization didn't need to test them because they were not promising at all. It tested only the combination that were more interesting, more promising to be tested. Now, before going on to the actual tutorial, where we will explore exactly how to use this optimization of hyperparameter strategy to your Kaggle competition problems, Kaggle competition challenges, let's talk briefly about LightGBM, because this is the target of our optimization today. You already know about ensemble algorithms. Ensembles are very effective in machine learning, and especially in Kaggle competitions, because no matter how complex is your classification or regression problem, it will help an ensemble to approximate better the curve that you need to derive from your data, so your mapping. Let's take the example presented in these two figures. You have actually two classes, and they are very near to each other and shaped both in a ring shape. If you take a single model, such as a decision tree, you will get the results presented in the leftmost panel. So you will just figure out a very rough way to represent a separation between these two classes. But if by backing, so by building different decision trees based on different combinations of different samplings of your data, you can approximate in the end a much clearer and much precise separation between these two classes. In particular, I mentioned you have two different strategies in doing so. One is bagging, which is basically a system of resamples from the data and then the combination of your algorithms, so training. Another one is boosting, and boosting is a different strategy based on sequential models, each one built on the results of a previous. So the ensemble is actually not guided by randomness, but guided by the results of a previous models. Gradient boosting is the most efficient way to do so, because actually it's a weighted summation between different models, each one built on the residuals, that is the error of the previous ones. Among gradient boost implementation, LightGBM is one of the most efficient ones. You may have heard of a recent histogram-based gradient boosting present in scikit-learn. You may have heard of XGBoost, of CutBoost, which are all very good implementation, very performing ones of gradient boosting itself. But LightGBM is one of the fastest and, of course, as the name implies, the less demanding memory algorithms that you can find when applying gradient boosting. It has been developed by a team at Microsoft, and they enhance the original algorithm by a series of strategies. For example, LightGBM treats in a particular way all the categorical data that you provide to it. And it also has a very particular, very peculiar strategy of building how it splits its decision trees, which are actually the single models that it sequentially builds. So in other gradient boosting solutions, actually, the trees are built level-wise. That is, there are some splits initially, and then each split is explored one after the other, creating usually, if you look at the tree as a graph, balanced trees, so balanced structures where you have an expansion in every direction of the exploration of possible splits on the variables. Instead, LightGBM just concentrate on the most promising splits, and it continues to split them until it's not necessary to go on. So at that point, it goes to explore other solutions. Sometimes this approach, which is called the leaf-wide tree growth approach of splitting decision trees, is more effective for many problems. In any case, it's very fast because since it concentrates on a single branching, it doesn't need to keep on switching between different portions of your data, and that makes it very fast and very effective. Anyway, in spite of all this very good advertising for LightGBM, tuning it may appear, if you just started working with this algorithm, quite daunting, because if you go and look at the number of parameters it has, you will find hundreds of them. Actually, please be sure that not all these are maybe impactful or useful for your problem. Just a few ones are. But even if a few ones, they are still quite a lot in respect of all the classical machine learning algorithms that you can test and try. So in our example tutorial, we will just focus on how to simplify this task for you by deciding on a very limited but significant number of parameters, and also by showing you how Bayesian optimization can prove quite effective in finding variety combinations without you to explore too much data and the algorithm by yourself. The tutorial is structured as RSI, and it is structured in 6 very simple steps that you can replicate for all the problems of machine learning you have to face and for all the competitions you are going to take on Kaggle. The first step regards preparing your data, especially your categorical data, because LightGBM has many others, gradient boosting based models can really take advantage of categorical data by treating it in a special way and a very effective one. Then the second point is related to defining your cross-validation strategy. The first step of the recipe regards defining your evaluation metric. So you have how to validate and actually how to measure your validation. Finally, you have to define your base model as a fourth step, and based on your model, define your hyperparameter search space. So the hyperparameters you are going to test and about what ranges of values you're going to test. And finally, you just run the optimization for a while. That is, you invest some time and computational energy to find a very good solution for it. I will present you the recipe, the tutorial in a few slides, but if you want to try it by yourself and experiment exactly how it works, you can take the Kaggle dataset and its related notebook at these two addresses, or you can just enlist on the original competition the data is based on and just run this other notebook. Both are working and both are presenting exactly what is illustrated in the following slides. A few words before starting with the code about the data and the problem we are trying to solve by LightGBM and Bayesian optimization. It is part of a competition, Pass 1, held by Amazon.com, and it was related to employee access to company resources. In a company, a lot of time and effort is spent on evaluating if a particular employee could have access to resources or to information inside the company. It's a problem of security, but it's also a problem of how to organize the work efficiently. And Amazon in 2010, 2011, gathered a lot of information in regard of the request that around the world it has got from its employees relative to access to its information and computational resources. And actually, the data is being labeled manually because all these procedures of allowance or denial have been run manually by security experts. Now your task is to take this data, the information you have, and figure out if you can create an algorithm that can replicate the work done by the experts in this time frame from Amazon.com. First of all, you have to know that your target is highly unbalanced, because usually when a resource is required, there are good grounds for it to be granted. So most of the targets are just one, so resource granted, and just a very few ones have been denials. Then, on the side of your predictors, you have to know that the information is basically discrete, is basically categorical. You have 9 features ranging from the resource code to everything about the employee role and position inside the company that could determine the allowance or denial of access. So you have a lot of categories in this case, and one of the first steps will be just to deal with them. Let's have a look at the code now. The first steps are relative to importing all the libraries, all the packages that you need for this task. Apart from NumPy and Pandas, basically you need the LightGBM, which is your prediction algorithm, and the Stumped functions. In particular, you need Bayesian, search cross-validated, the optimization engine. You need the callbacks, which are functions that can help you during the Bayesian search. And you need a few functions called real, categorical, and integer that can help you to sample, as in a random sample, from the space of the hyperparameters values. You can get all these packages pre-installed in Kaggle kernels. The notebooks are already set up for having all these packages. In case, I provided to you all the pip install commands that can help you to set up the same configuration on your own computer. After importing the useful packages for this tutorial, you have to get the data and to prepare it. This is done very easily. Basically, you have a loading phase using pandas red CSV, and then you just have a few actions. First of all, separating the target from the predictors, and then separating the identifier from the test data, because actually you have the identifier on the test but not on the train. And then you have just to convert all the integer variables to categorical, which is easily done just picking this each single column and transforming it using the asType method and specify it should be a category. This data also provides a few more challenge that maybe you cannot have on your specific data sets or your specific problems, but you have to be aware of this problem. If you look at and inspect the data, you will find out that the categories are sparse. It means that as we, for example, noticed before, as far as the resources, you don't have so many resources. You have a few thousand elements. But if you look at the numbers representing them, they're very high. It means they're very sparse. Even if LightGBM is a very performing algorithm, it won't work properly with all such sparse categories. Categories have to range from 0 to the number of categories you have, and they should all be discrete numbers, continuous ones. So the following 4 cycles just have the purpose to take each integer column and just find out its unique values and remap them in a way that they are continuous, one after the other. So that's all. And you have to check also in your dataset you have similar problems, but they're quite rare, so probably you won't have. Sometimes instead you can have situation where your categoricals are expressed by string values. In that case, a label encoder from Scikit-learn will just provide to you the right numeric labels. After preparing your data, so it's first a part of a recipe, I propose to you this very simple wrapper, which later will prove very useful in reporting to you the results from Bayesian optimizations. Basically, you can run each one of these commands in line or as separate commands. But having them in a wrapper is very convenient, because basically all you have to do when you are optimizing, no matter the problem, are always the same steps. You need the optimizer, you need your data, your target, you need a title, of course, for your optimization effort, and you need the callbacks. And then what you expect is just to have a report of the time spent, and of course, of a best score that the optimizer has found, and of the hyperparameters that has provided to you. So this wrapper is very useful for all your efforts on Kaggle, and you can reuse it, or you can just pick the single comments in it and reuse them in another, flow code. After defining the wrapping function that can help you to record the best results by Bayesian optimization, let's complete our recipe by providing the metric for evaluation, the cross-validation, of course, your base model. As far as the evaluation function, in this case, our problem requires a measure to be maximized, the rock RC, so the area under the curve, around the rock curve. And since Bayesian optimization works by minimization, it is a very good practice, of course, to know about your evaluation metric, but also to transform it using the makescorer function from scikit-learn, which will convert all your evaluation metrics, no matter they are, for minimization or maximization, in a unique way. So it's kind of a metric standardization, and for running it, it's just necessary to provide the original metric and to provide information about if greater is better, and if it is probability based, and in case it is not probability based, but you are providing probabilities, if it needs a threshold to decide the prediction. And after doing that, also you have to set a fivefold cross-validation. In this case, we use a stratified one, because we want to control the fact that our target is actually very unbalanced. So we really want that for everyone to have a good and enough proportion of our target, so our modeling will be meaningful. And finally, we set up our base model, which is a LightGBM classifier. Here we have very little to say, apart that you have the option that, of course, you can set multi-threading and multi-processing, but if you are running Bayesian optimization, let's just the optimizer do the parallel jobs for you. So to arrange its parallel operations, and here you just have to set for the classifier not to use parallel jobs, but just a single job. And other noticeable things is the boosting type. Here we just choose the gradient boosting classical approach based on decision trees, but you have other options. We are not going to explore them today. And your objective, which in this case is binary, you can also choose regression, and of course multi-classification depending on your problem. In this case, it's just binary. And finally, the last part of the recipe is the search spaces. And here you have a number of hyperparameters for LightGBM that we know they are very effective and important to optimize. First of all, you have the learning rate. The learning rate is, let's call it the speed at which your LightGBM will learn. Of course, the speedier, the less precise will be. But if you are really taking two small steps, it can take a really long time before your optimization arrives. So your good results arrives. And number of estimators, so is the number of boosted trees that they are summed in the ensemble. The maximum number of leaves for the base learners, so you impose a constraint on the complexity of the decision trees, the same as for max depth is another way to impose complexity restraint on your algorithm. The mean child samples, which has the same effect as the previous two, It reduces the complexity, but also it is something related to the statistical representativeness of your model. It means that you expect every child sample to be at least at a minimal sample size. It means you are expecting that your results should be determined by a certain numerosity, and you won't accept, results for leaves of your decision tree that are less than a certain number of examples. And then you have max bin, which is the number of bins that each feature will be discretized into, because basically LightGBM can boost its efficiency by using a system called histogram based. So every numeric feature will be reduced to a certain number of bins, so a certain number of intervals of its numerical range. And the algorithm will use the histogram based on that numbers of bins. Of course, the larger the bins, the more precise, but of course, the more memory will take, and the less efficient in terms of time and memory the algorithm will be. And then you have some probabilistic hyperparameters, subsample and subsample frequency called sample by tree, which actually are representing how you are sampled from examples and from features in order to have a more stochastic approach to your estimation with LightGBM. Finally, the minimum child weight, so it's the minimum sum of instances weight, the action needed in a child, which is something related again to complexity. You have a regularization in terms of L2, the lambda parameter, and L1, the alpha 1. And finally, the scale post weight, which is just for classification, which is the number, the multiplier for the minority class in order to work better. The search space, of course, that you post to you is valid for all other problems that you may take on during your Kaggle competition. And personally, it's the search space that I use for most of the problems I face, both at work and doing competitions. So you can rely on this sampling scheme for all your optimization problems related to LightGBM. At this point, you just have to set your Bayesian search cross-validation. So you provide your base model, your search spaces to this function, your evaluation metric, and your cross-validation scheme. After doing that, you just have to decide the maximum number of iterations to be taken. I suggest giving it a very high number and then deciding on the stop based on the time you have. Basically, in every Kaggle competition, you have a limited time. You have to provide your optimizations and your submission in a short time. And under such time constraint, it is important to control how you optimize by defining exactly the time you want to spend in order to improve your results and nothing more. And then you can define with endpoints parameter, this Bayesian search CV, also the number of points of experiment trials or combination that the algorithm can explore simultaneously. And of course, you can provide multi-threading, multi-parallel opportunity to the algorithm by setting the number of jobs to -1, which means taking everything, all resources possible to produce the results. The following parameter, the IID, it's something that related to how the Bayesian optimization treats its results. By putting it false, it means that you are optimizing basically for the cross-validation score. The alternative is putting it to true. In this case, it will consider the out-of-fold results. But we actually suggest you not to do so. Instead, to optimize based on the cross-validation. So to make an average of all the cross-validation metrics results, because this has a more predictive valence in respect of your problem. So it can tell you in a much better way what your algorithm could perform, could do with unseen test data. So we strongly suggest that. Since we are doing everything by a wrapper and we want in the end to retrain on all the data, not on by ourselves and not let the algorithms do so, we just put refit is false. So this also will save time for our Bayesian search. And finally, we provide the optimizer information. So it's GP, the Gaussian process, the algorithm we detailed before, providing to you estimates, so your surrogate function, but also your acquisition function, because it is just the uncertainty that the algorithm produces in its predictions. And at this point, you are practically ready to go. You just set two callbacks. The first one is the delta y stopper, which tells the Bayesian optimization to stop if it cannot see any furthermore improvements, because as we described before, it's always a game of finding a better optimization. So finding out a better way to optimize could mean to test very slightly changes of your hyperparameters, which could bring some gain, but at a certain point the gain would not be meaningful anymore, and you prefer to retrieve your time instead. And so we just put a stop when, of course, improvements are very, very slight. And a time control. In this case, we set that the maximum allowed time is 45 minutes. You have to express by the deadline stopper this value in seconds. So just 60 seconds for 45 times. So it's 45 minutes. And then you just call the wrapper performance, the wrapper, and the optimization will be executed to you under 1 hour time. And the results are actually very good, because it can just achieve a 0.862 cross-validation score in a very short time. And here you can get all your best hyperparameters that you can use in retraining the model and then submitting it. Our tutorial has been quite short, quite to the point in showing to you a very simple recipe. Take your data, clean it, prepare it, separate the target from your predictors, make it uniform with your test data, and then you just have to settle your base predictor, your cross-validation schema, your evaluation metric, and just put everything together into a Bayesian optimizer provided by Scikit-optimize, run it for a certain time, the time you want to spend in optimization, and get the best results. But actually there's even much more. And there's another tutorial, which is a longer one. You can have also the video about this, which has been presented in Paris during the Kaggle days in 2019, which is also using the same Scikit-optimize Bayesian optimization algorithm, how to run optimization step by step. So basically just be there, running each iteration of algorithm by hand, by yourself, using it for neural architecture search, so also for deep learning, so optimizing your networks by using the same procedure, making some adjustment to the Gaussian process engine. So basically, since it is a machine learning algorithm, it has parameters itself, and you can optimize them. And also using random search to refine especially the starting point of your Gaussian process. When you have quite a lot of hyperparameters, Gaussian process, in a Bayesian optimization has some difficulties at the beginning, finding out the areas where to explore. Running a random search first, maybe a limited one, can provide already a basic search space explored for the algorithm of Bayesian optimization to work much better. And you can find all these with examples, not limited to LightGBM, but extended to XGBoost and CatBoost, and of course the standard Gaussian boosting for scikit-learn at the following address. So I thank you very much for following, and I wish you good Bayesian optimization and good luck with your Kaggle challenge. I hope that this tutorial could enlighten you of a various way to optimize hyperparameters, and especially as persuaded you how to use Scikit-optimize for such a task. Thank you. Thank you very much.